We've been dealing a lot with rockets flying in free space. That's how we developed the rocket equation. But when we launch rockets from the Earth, we're not flying in free space, at least not at the beginning. We have to fly through the Earth's atmosphere, and of course we have to fly up through Earth's gravity field. So let's just very briefly look at the impacts of flying through an atmosphere and doing work against gravity. Here's a typical launch of the space shuttle. We've seen it many times. Normally, you only get these close-up images when the shuttle or any other rocket that's taking off is fairly close to the ground. Beautiful launch, here it goes, and pretty soon it will disappear from view, unless you're looking through a telephoto lens which can track the spacecraft as it goes up. And here's what happens. At about 50 seconds into launch, you're still going pretty much straight up. You got a lot of power coming out of those solid rocket boosters, and you're accelerating, and you actually break the sound barrier. That's Mach 1 at about 50 seconds or so into flight. And you can see here the actual shock waves that are emanating from both the shuttle and the whole stack of the boosters and the external tank. At this point, it gets to be a pretty rough ride, and there's a lot of vibration. The shuttle stack on top of the external tank is not particularly aerodynamic, and so you got a lot of shock waves bouncing around between the belly of the shuttle and the external tank. That's right kind of in here. And that gives you an even rougher ride. We talked before about how all of the turbulence inside the solid booster rockets gives you a lot of vibration, but going through Mach 1, the vibration level increases tremendously. Why does that happen? Well, because of dynamic pressure. The actual pressure that a vehicle feels flying through the atmosphere depends both on the thickness of the atmosphere, which of course depends on the height, because the atmosphere gets thinner as you get higher, but also on the velocity with which you're flying. The faster you're flying, the greater the dynamic pressure. And in fact, the velocity dependence is as the square of the velocity. The dependence on air density is just the first power. You multiply those two together and you get the dynamic pressure. And what happens is, initially, the velocity is increasing faster than the air pressure is decreasing, so the total dynamic pressure rises. It gets up to a maximum point, and now you're getting high enough up in the atmosphere that the air pressure is falling off so fast that even the fact that you're continuing to gain velocity doesn't overcompensate, and in fact the total dynamic pressure starts to decrease. Here's a diagram of that. This was taken from an Apollo launch. So the pressure times the velocity squared for a while increases until you reach a maximum, and this is what we call max Q, with Q being the dynamic pressure. And then as you get up higher, of course, the velocity continues to increase, but the dynamic pressure decreases. And it's at this maximum dynamic pressure that the whole stack is at the greatest structural risk. And that's why with the space shuttle, we actually throttled down both the liquid engines to about 70% of their top performance, and even the solids, because of the star pattern, which we saw a picture of in an earlier part of the lecture. That actually decreases the thrust of the solid engine so that the integrity of the stack is protected.